Today I'll be joined by Adam Zsarnóczy, Dr. Adam Zsarnóczy, who's the Associate Director for Outreach, Research Outreach with the SimCenter, and also Pedro Arduino, a faculty member at University of Washington. Oops. So what I'll begin with today is to give you an overview of some of the SimCenter tools and resources. Some of you may be familiar, but introduce them to others. And then we're going to spend time, myself, Adam, and Pedro, talking about three different applications where our SimCenter research tools have been used in different types of class courses. I should point out that these tools we originally developed, and they are intended for research, but what we found over the years is that bringing them into graduate level class was a great way to expose students to some kind of leading edge sort of technologies and computational workflows and new sorts of models. And it also has the benefit then of these students can take it into their own research or projects, or those, in fact, some go into industry, have used them, have taken some of these ideas and applied them in practice. So let's get started, and we're going to have time at the end for questions and discussion. So I'd ask everybody to, if you have questions as we go along, jot a note to yourself so then we could get back to those when we get through our presentations. So just looking broadly at the SimCenter applications framework, we're really looking at natural hazards engineering. Today, we're going to focus on earthquake engineering, but also we're looking at things like hurricane, wind, and storm surge, tsunami. But we want to imagine computational workflows where we could stitch together existing information and models, say information on assets in a community, how we describe the hazard, how we do computational modeling, damage, loss, and all the way to recovery. And so the idea is by putting these workflows together, we're enabling people to address larger problems in a quicker, more expedient way to kind of lower the bar to entry. So what we developed over the last 8 years has been a number of modules. And at the lowest level of this kind of pyramid that you see here are a number of software modules. Some of these are computational algorithms, others are APIs that connect out to outside databases. And we can use these through Python coding to stitch these together. But then we have a number of kind of desktop applications. And these are some of the ones that we've pulled into classes because they are basically menu driven. So they kind of make it easier for new users to kind of make use of these workflows. The first one, QuoFem, we'll talk about that, couples kind of computational modeling with methods of uncertainty, uncertainty quantification, optimization. The next level up is we take those sort of capabilities in QuoFem and we link them with information from hazards, earthquake, wind, hydrodynamic hazards. And finally, going a level up from that, we'll take the output of simulating structures and soils and sites and so forth and look at performance-based engineering, what's going to be the damage and loss of individual facilities. And finally, the last tool we have really pulls this all together in looking at regional risk, large inventories of buildings and transportation networks. So I'll talk just about a few of the tools that are kind of featured in some of the teaching modules we'll talk about. The first one is QuoFem, and this is one that links various types of ways to simulate structures and facilities, could be CFD, structural analysis tools, with engines for uncertainty quantification. And what this allows users to do is they could take analyses and propagate uncertainties through them. They could look at sensitivity of response to the input parameters, reliability analyses, or increasingly of interest is using machine learning techniques to make surrogate modeling. Another way, though, with the optimization algorithms is to use the same sort of statistical methods to optimize parameters by which you can take a computational model, compare it to an experiment, and it optimizes the process of fine-tuning those parameters. And that's, in fact, one of the modules that we'll talk about. Next, if we look at EEUQ, so that kind of takes the capabilities I just described from QuoFem, but we have APIs that link it into hazard information to look at OpenSHA at the USGS to characterize hazards at specific sites in the US. OpenQuake does that worldwide. And then linking it into online databases of recorded and also simulated ground motions, linking those with our structural models. And EEUQ also has features for automatically developing certain structural models of frame type structures. So one can do parameter studies. And then the idea is you could then apply this to propagate uncertainties with ground motions, develop surrogate models. So that's the EEUQ. Next, moving up to performance-based engineering, this is focused on taking the output on structural response and coupling with damage and loss models, where again, we have kind of the input coming in, the structural demand, coupling it with these damage and loss models, and then making estimates of damage, repair costs, repair times, and coupling this into some recovery type models, looking at topics in functional recovery. And again, this is looking at an individual asset in different levels of fidelity or resolution. And finally, we could pull these sorts of models forward into the R2D. This is the regional tool. This is built on a QGIS platform where we're basically geocoding various types of facilities, information on networks, and also the hazard information. And increasingly, when you look at kind of some of the social questions of the implications of hazards, there could be databases of demographics of communities that are coupled. So this pulls those together. And it allows then one to look at, multiple types of hazards. Again, we're focused today on earthquake, multiple types of assets, and different levels of resolution. The idea with all of these tools is that one can mix and match different types of models. So for example, you could have low resolution of all the buildings or facilities in a community, and then higher resolution of a few critical facilities. So that's the key feature, that flexibility that's built into these models. Okay, so that's kind of a quick snapshot. There's information on a lot of this information. If you go to our website at the SimCenter, kind of everything we produce should be accessible to you there. You could download the software. We have GitHub repositories with the source code. Everything is open source. Documentation is up there, in addition to a number of various webinars and trainings that we've done throughout the year. So I'd encourage you, if you haven't already, to take advantage of looking at that. We also have one of the links there under Join the Community, a forum where you can kind of offer comments and questions, suggestions on specific applications that we have. Okay, one of the key things we have, and we'll kind of talk about today under the Knowledge Hub, is a teaching gallery. So this is these are little modules that have been developed by faculty using SimCenter tools in their classes, and there's a collection of about 6 or 7 of these now, and we're hoping to sort of build that as faculty are using the tools and want to take a little bit extra effort to build it in a module that we could post and share on our website. These teaching gallery modules, we want it to be a low bar to contribute one, but we do want to have a structure to it. So it provides, each of these modules has a little bit of introduction to the module, what it's about, what's the context, what kind of class the faculty member was using this in, what kind of tools they're using, what are the learning objectives from it. And then there's a number of supporting information, slides or videos that the faculty has put together in the course of offering this. And they're typically organized around some sort of an exercise, could be like a homework or an extended homework that might have a tutorial aspect, and of course, then supporting information. And just as an example, this is one for uncertainty in nonlinear structural analysis of structures. This is a snapshot of what you'll see when you go to the teaching module. And again, what I wanted to just draw attention to is the types of documents that are given there, the ones I just described, kind of the module prompt, background slides, because we anticipate these are small modules that faculty can integrate into their own class, but they might want to do it slightly different than someone else has done it. So the slides are there in PowerPoint form, so faculty can take those and adapt them, modify them as they'd like, or they could use it just as been presented. And we have kind of videos presenting those slides and how it's actually been used in classes. There's also the supporting code. You see some snips of the Python coding shown on the right. Okay, so that's kind of an overview of kind of tools and these modules as they're presented on the SimCenter website. Now I'd like to talk about some things that I've done in a nonlinear structural analysis class, and this also would have applications to other classes like that or in earthquake engineering. And here I'll be using QuoFem and the EEUQ tools. I included here the syllabus for my class just to give you an idea of how I approach this. I've been teaching nonlinear analysis for many years, and I had a well-developed syllabus. And I always hesitated bringing in a tool like OpenSeas just because the extra effort it would take to teach students how to use OpenSeas and then to do other exercises with it. But with some of the SimCenter tools, I got brave enough to put a few modules, and these are the ones that are shown in red. Just this past year, one on structural fire engineering using OpenSeas that I introduced. And I had to kind of squeeze these in, so it's not an easy lift necessarily, squeeze these into an already full syllabus. But just to talk about the modules that I introduced, one was using OpenSeas on Colab, which really lowers the bar. There's no installation necessary. Students can run the Python version of OpenSeas online. And then a few examples of where we're using EEUQ and QuoFem for pushover analysis, nonlinear dynamic analysis, parameter calibration, and as I mentioned, this latest module on fire. So I'm just going to talk in detail about two of these, the uncertainty quantification and the nonlinear dynamic analysis. So the first I'll talk about is the parameter calibration. The motivation for this is that a lot of the natural hazards engineering research infrastructure, NEARI, are experimental facilities. And the idea when one wants to bring these into computational models, how they can calibrate the parameters of those models to the experimental data. This is just an example of a large shake table test that was done at San Diego some years ago under multiple ground motions. This was actually used in blind prediction analyses. And kind of what's shown in the lower right is kind of a scatter plot of what the structural response is compared to the results of 20 or so people who entered the blind prediction contest, just showing the great variability in assumptions people can make in terms about matching data. So we hope that these tools on semi-automating the calibration can really help on kind of narrowing down the variability we see in how people are simulating experiments. So the example we did in my class was to take went to the peer database as a collection of many reinforced concrete beam columns that have been tested. We took out one of those that's relatively simple. And so the idea, this is the experimental data. We then create an OpenSeas model, and this is one element. So it's a pretty simple model, but there's still, it illustrates a lot of the challenges on parameter calibration. So you can see an idealized picture of the model up there. We put this in OpenSeas Pi, and there's kind of three parameters that we want to calibrate: the initial stiffness and two of the strengths of the member, to automatically use the QuoFem tools to calibrate that to the data. So the goal again is to get an optimal set of the parameters whereby our simulations can match the data closely. And of course, people have done this before. Typically, they've done it kind of in an ad hoc way by making estimates of the parameters, seeing how the response varies, and then just manually going through that. What we're doing here is we're coupling the OpenSeas tool with a uncertainty quantification and optimization algorithms that's in a toolkit called Dakota, developed by the national labs. And so the features of QuoFem in this particular study, we could do a parametric study. Probably the first thing one wants to do on a calibration is just explore the sensitivity of the response to variations in the parameters. We could then do a conventional calibration. This is one that's kind of deterministic, that's using a gradient search method to optimize the way to get those parameters, and then a Bayesian calibration. And what's shown on the right are some pictures from kind of classic optimization things. Part of this exercise in class is just to introduce or remind students to the idea of gradient search algorithms, and the fact also that when you have multiple parameters, there's sometimes not a unique answer. And so these are things one needs to be aware of when they're starting to use these automated calibration tools. So in this example, we went through and with the students and talked about, okay, how would you set up an objective function? We have the load displacement response shown on the right, and there's a fixed displacement loading protocol. So the error is going to be measured relative to the forces over time. So that sets up our objective function. And basically, we want to minimize the error there. And then what's shown in the scatter plot in the center is basically the output from what we could do in QuoFem. We could ask it to do a sensitivity study where it'll plug in a bunch of variables and get outputs, and then it has the error that's sort of color-coded. We could then use the automated routine, the deterministic calibration, does a gradient search algorithm, and in about 12 iterations, you can see the black trace there, we get to kind of the optimal condition or near optimal that's shown on the right, the agreement between the experimental and the simulated data. And you could also then look at some of these other cases that are far from being optimal and just get an idea of how the different parameters, and when we look at this error index, what a value of the error, how it translates into what the load deflection behavior looks like. So we think this is valuable to kind of introduce students to tools, or maybe they've seen them in other classes, but to apply them in this context. And QuiltFEM is really facilitating doing that quite easily, lowering the bar. QuiltFEM also has a Bayesian calibration, which requires many more iterations. And what this has the advantage of is, instead of coming out with one set of optimal parameters, it gives a distribution of plausible parameters, the parameters I mentioned, the strength of the member and the stiffness and so forth. And in fact, if one's thinking of uncertainty propagation going forward, having these sort of distributions is kind of very helpful, and it helps kind of narrow in the sensitivity of the results. And if you run the Bayesian far enough, you'll get a mean value that's probably a little bit off from our deterministic calibration, and arguably is more kind of precise, if you will, answer. Okay, so that was the one example. The next one I want to talk about is how we used the EEUQ to do nonlinear dynamic analyses. And for me, the motivation of this is that in engineering practice over the last 10 or 15 years, nonlinear dynamic analysis has gone from a research tool to one that engineers are applying for special cases. And those documents that are shown on the left are ones that outline procedures. And in fact, there's nowadays tall buildings on the west coast of California routinely will do a nonlinear dynamic analysis. So that was kind of the motivation for bringing this into the class. The reason I'd not done it previously is I'm teaching nonlinear analysis. So we're building nonlinear models of structures. But then if we want to do a nonlinear dynamic analysis, I have to talk about response spectrum and how you select and scale ground motions and how you perform nonlinear dynamic analyses, and then producing results. And this was, without some tools to help facilitate this, it's a pretty heavy lift to interject into my class. But so what we're going to do in this example is we're using OpenCs to create a numerical model. So that's the main focus of my course. But then we're using EEUQ to facilitate getting the response spectrum targets, selecting and scaling ground motions, and then sort of running the analyses. And then we provide the students with a set of Python scripts that we give them to collect and parse the results. Because this, again, I built into something that's essentially a homework problem. Students have one class on this, then they go home and they work on this, and it's a week-long homework. So just the different parts of that, we'll use, again, OpenCs, and we give them the OpenC structural model, because, again, going through the Tcl or the Python commands to build that's a little bit of heavy lift, but we give them that model, but we describe what's inside of that model, so they see the parameters and they could look at our code and understand how everything's defined. Then the key part of doing the nonlinear response history is defining a response spectra and ground motions. And this is where folks do this in research routinely, but it's kind of a heavy lift to explain it to a class of master students who are new to the topic. What's shown on the right is a snapshot from the page from EEUQ, the application, and it has an API that can immediately reach out to the USGS national hazard maps and seismic hazard information, where one can put in a building site and automatically pull in different types of response spectra, conditional spectra, uniform hazard spectra, which we could describe what they are, but it basically cuts out the work of kind of figuring out where that site is and how you download that information. And then given that target spectra, we have another API where we could reach out to the peer ground motion database. This is a ground motion database with tens of thousands of ground motions. We have a selection algorithm built into EEUQ that can go through that database and pick a number of ground motions that match that target spectrum. And these ground motions can then be applied in the structural analysis model. EEUQ can run that, get some of the results, but then we also provide some Python code, and this we find it's handy to give the students Colab, where they could take the results of their analysis, copy it into Colab, and then we kind of have some suggestions on how they could plot different response quantities. Okay, so that sort of is a snapshot. I think I just wanted to mention that, again, what I found compelling about this is we can explore topics that were otherwise out of reach in the course I was teaching: optimization, UQ, propagation, dynamic analyses. You know, there are some challenges to this. I mean, I won't say that it's learning these new technologies is not totally trivial. You got to, both the faculty member, their teaching assistant, and the students have to put some effort in. one has to think about how to integrate this into their course. But I think in the end, students responded really powerfully to this. It really empowers them to do, there's course projects that they did in this class where some of the students have used these tools. They've gone on to use them in their research and in some cases in engineering practice. Okay, with that, I'm going to turn it over to Adam, who's going to talk about some modules related to performance-based engineering. And again, we'll kind of hold questions, so I'd encourage you to make some notes and we can come back for questions and discussion at the end.
Thank you, Greg. Just want to make sure that you see the right screen.
Yeah, we're
seeing. Confirmed.
Yeah.
Thank you. So as Greg mentioned, we are switching gears a little bit and continuing with kind of the next step in a risk assessment workflow, which would be assessing the performance of the structure, and then even going further and looking at multiple structures or portfolios of structures. Before looking at the specific examples, I wanted to take a step back and just revisit this page that Greg showed about 20 minutes ago. So we have this PBE tool that is focusing on damage and loss assessment, but it's not limited. I will have many examples that are earthquakes and buildings, but the tool itself is not limited to that. So if you are involved in, or you are teaching a course that is focusing on something other than buildings or some other type of hazard, keep in mind that PBE will be able to handle those as long as you have a assessment that that deals with those kinds of things and you have the corresponding data available. So we are doing this damage and loss assessment using demands either from EEUQ, that's directly integrated into the PBE tool, or you can bring your own demands that could be coming from another earthquake-related tool like ETABS, or it could come from other types of tools that might assess the demands under other types of natural hazards. And then once you have the damage and loss simulation performed, you can move on and use the detailed output provided by PBE to do something like functional recovery simulation, or perhaps other types of post-processing and further simulations with the results. Most of the time, as I mentioned, this tool is used in classes for FEMA P58 style assessments, so high resolution seismic performance assessment, where PBE covers the green shaded area of this peer framework. So it does the response distribution simulation, then simulates the damage, assigns damage states to specific components in the building, and then looks at the consequences of that damage and then quantifies the losses. That's the typical use case that we see in courses. And I will show a couple of examples of different ways people leverage these capabilities in their courses, so that I think you will see the breadth of kind of like a menu of what is available, and I hope that will spark some ideas on your side. The first is a simple case. It's from Stanford University. Jack Baker is teaching this class now. It used to be taught by Ankira Midjan. This is a broad risk and seismic hazard related class that doesn't really go into the details of FEMA P58, but rather provides an overview of seismic hazard and risk analysis. As such a class, they find value in a PBE because it provides an example for the students without having to go into the details of teaching them how to perform a FEMA P58 analysis. So this is similar to what Greg mentioned earlier about how ground motion record selection was helpful to bring in without teaching all the details of it. And we provide students with a starter package that has all the inputs and all the models predefined, so that they can start PBE, they can use the graphical user interface and just load in the models. You can see here we have a lot of components, component quantities, all of those are predefined for the students. And then what they are asked is to provide a few inputs, just so that they have to look at the models, they have to look at the building, they have to think about it. For example, they have to assess the replacement cost of the building, but everything else is provided. And then they look at the outputs and do some high level interpretation of what comes out of such a method. Then in this particular class, they are comparing this approach to something like HAZUS, which is a simpler model, and then look at how the results are similar or different, and are able to put this in their head and think about PBE as an option for their future. A lot of students from this class ended up going deeper into PBE, taking another class that is specifically focused on that, and then using the PBE tool in their research at Stanford. So it's, even though it's a really simple and small assignment, it can have a big impact on the students' future, either in research or industry. We also have examples who went into industry and then use this in their work. In a course where you want to go deeper into FEMA P58, you might think about integrating PBE more thoroughly into the course. The one taught at UC Berkeley by Tracy Becker and Andreas Schellenberg is an example I brought here today. They are looking at the seismic evaluation of an existing building, and they teach ASC 41 and FEMA P58 both in this course. So they really want students to be able to perform these analyses themselves. And here, what we provide in their starter package is more of an example, more of a template kind of thing, which they can then use to create their own models and run their own analysis. Again, the user interface is helpful because they see the fragility functions, they see the consequence functions, they are able to graphically and visually observe the kind of components that are assigned to the building, the quantities that they assigned, and they are able to quickly run an analysis, see how certain decisions they made in the modeling affect the results, and then iterate very easily. So that's something I believe the students appreciate. They are also able to use results from external nonlinear analysis. They use STAP or ETABS to do the nonlinear analysis, and then they bring in the engineering demand parameters that come from those and continue only for performance assessment in PBE. So this is a possibility. And again, as I mentioned, this is not limited to seismic cases. You can do a wind-related study just like that. You bring in the EDPs, you bring in your fragility functions, and then you can do the calculations there. And another part that is important is that these students have to discuss the vulnerabilities of those buildings and potential ideas on how to retrofit them. This detailed output that is provided by PBE is really helpful for them. They can look at the component quantities, they can look at the demands, the damage, and the decision variables in every possible detail that is available from the calculations. So they can really go deep and see how certain decisions made in the modeling and perhaps certain retrofit actions would affect the performance of the building. Here I have my third example from the University of British Columbia, which is similar to the previous one in how thorough the course covers FEMA P58. The course even goes into functional recovery simulation. The difference is that Carlos Molina-Hutt is not using our PBE tool, but rather uses the underlying engine Pelican. And I wanted to mention this as an option for those who already have a pretty solid workflow, maybe an algorithm, maybe a script that they share with their students, and you don't want to introduce a new tool with a graphical user interface. It might feel like too much of a hurdle. So you can use Pelican and just run it from your existing script. The students don't need to know much about what is happening there, except for what kind of inputs they need to provide and then processing the outputs. This is what Carlos has been doing for a number of years. You can do this through the command line or in a MATLAB code or even through Google Colab online. The benefit is how seamlessly it is embedded. The price you pay is that the students will not be able to take advantage of those user interface provided ease of defining the models. So they don't see the fragility function, they don't really see what is happening. So there's a price to pay, but if that's what you are interested in, this is also available. And in this last example, I would like to show how we can go beyond what is available in FEMA P58. So you might want to do a high resolution assessment, but not exactly the way it is described or not exactly with the components that are provided by FEMA P58. This is coming from Texas A&M. Maria Koliu has been adopting the tool for something like this. She's interested in showing the students a little broader seismic performance and risk assessment related topics. So she doesn't limit the scope to FEMA P58. And another interesting part of this is that she doesn't have a TA. So she was able to adopt this course without having a TA, which I believe those of you who don't have a TA know how much more challenging it is for a professor to make such changes to an existing syllabus by themselves. So what's special about this course is that she shows a case study where she's looking at a structure that you can see on the picture. So it's like a big mall kind of building. And she also wants to include non-structural components like HVAC and contents like storage racks, just examples. So this is not a comprehensive study. We don't go with like 40 different components. It's just to give students a flavor of how this could work. And the structural fragility comes from Maria's own work. So that's a custom fragility function. It's not part of P58. And the other two functions are also something we got from literature. And we could prepare these as custom inputs to PBE and provide them to the students, so the students don't have to worry about how to get those fragilities, but they understand that those are custom and specific to the building and the type of components in the building. And they can focus on only like simple, small tasks, similar to what I mentioned for the Stanford course earlier. They just need to understand how many of these components are in a building and where the building is located so that they can get the input demands. And this way they can assess the losses in a building like this. But what's really exciting about this course is the next assignment that's built on top of this, where each student has prepared already a building analysis and the corresponding model. And then we combine them into a portfolio of buildings. So now we are looking at, I believe it was 18 malls in Los Angeles. We located actual malls in the city, and that's where the yellow dots are. And then we wanted to see how this portfolio of 18 malls, let's imagine they belong to the same chain, is affected or would be affected by different earthquake scenarios. So we gave students 6 different scenarios. The students were forming like different groups, and then each group looked at the entire portfolio and discussed how that each particular seismic scenario affects the losses and how they are different. They came together for a class where they shared their findings. And Maria told me that it was very interesting for the students to see how much the scenario they picked influenced the results and how different their takeaways were now that they are looking at the entire portfolio compared to when they were looking at an individual building. Now, what's interesting here is that they used R2D, and again, R2D along the same lines of what I told about PBE, allowed Maria to provide the students as much as possible in terms of pre-configuring the simulation, pre-configuring most of the inputs. So the student didn't have to worry about how to do the details of this analysis, but they still could take away a lot of good learning on how portfolio risk analysis is different from individual building risk analysis. And they could do all of this within the tool. So R2D provides this user interface with a GIS, QGIS built in. So you can look at the buildings, you can look at the contours of the ground motion, of the ground shaking, and you can look at individual building results as well as the portfolio results. So as long as the class has such a simple objective, you will be able to have the students achieve it within the tool. And then if you have a more ambitious class, of course, you can still do the kind of post-processing that I mentioned for PBE. Now, R2D can do a lot more, as Greg mentioned at the beginning, and we are exploring with instructors how it could be adopted for other classes that deal with risk assessment. We are having a couple of meetings this summer to see what are the needs of different instructors in the country. And I mention this because if any of you are interested in joining these discussions, please let me know, and then we are happy to invite you to the table there. And our intended outcome is additional teaching modules that will show these additional use cases with R2D, which go hopefully beyond just buildings and beyond just seismic cases. So you will be able to see the potential and the versatility of this tool. I would like to close with reiterating how much support we can provide for instructors. There is the teaching gallery, of course. Several courses that I mentioned are either already available or they are going to be available in the next week or two. in the teaching gallery related to PV and R2D. And then if you are interested to bring this into your course, we can provide you dedicated support. So one-on-one discussion on how these tools would work with your course and what are the capabilities, and trying to help you bring those into the classroom. Then we can provide a getting started lecture for your students, either in person or virtually. If you are not too far from where we are, then we can do it in person. And besides the tool training videos, we can also provide dedicated office hours with one of our staff members that can sit with your students, again, either virtually or in person, to look at technical issues that they might face and make sure that they are not hitting any obstacles as they are dealing with your assignment. And with that, I will hand it to Pedro for the last part of our webinar. Thank you.
My name is Pedro Arduino, and as a last presentation here, I want to share with you the outcomes of an exercise that we did at the University of Washington that was to have a whole course on SimCenter application tools. So the title of the course was An Introduction to NERI SimCenter Tools and Design Safe Resources. So instead of just bringing a module to a course, we wanted to have a full course introducing all of these tools. So this is the syllabus, similar to what Greg mentioned of the class. And I just wanted to mention a couple of things. First, we had to limit to a few of the tools that provide SimCenter. So we look at QFM, EUQ, and R2D, and Brails. Going into this, we knew that we were going to have some hiccups with some of the tools. So we decided to create a living Google document where we would post some of the comments, some of the ideas, some of our experiences, so that they could be useful for SimCenter. And also going into this, I knew that I was going to need the help from all the SimCenter postdocs for many situations where we wanted to do this or that, how to do that. And I had to acknowledge that without them, the course would have been a complete failure. But because of them, I thought it was a success. The course also included a document, a project document, where the students had to build some activity using some of the tools, and they have to produce a document that we wanted to share. So with that, I want to go into some of the exercises we did for each one of these tools, and at the end, I want to show it with the document that we produce. The first idea is that I wanted to go into QFM. We wanted to explain how QFM works. And I wanted to do that with a very simple example, something that the students were very familiar with, something they were comfortable. So we look at settlements. So settlements calculations are very easy to do. I have to mention something else. Most of my students were geotechnical students. So our applications were geotechnical applications. And I had around 10 students. That's why this equation for them was absolutely something very familiar. So now when you look at this equation, you see a lot of parameters. And of course, what we wanted to add is a little bit of the uncertainty in these parameters. And that's why QFM became a very good tool. When you include uncertainties, then we can do propagation. Propagation was the settlement. And of course, the settlement is not one value. You have a distribution of possible values that you can get using QFM. The second thing that I wanted to do with QFM is, yes, I can do propagation. Can I do sensitivity? And yes, you can do sensitivity to look which one of all this list of parameters is the most relevant for the settlement calculation. And immediately we notice that some of the graphical aspects of the QFM could be a little bit limited. Can we present this in a different way? And that's why I found the benefit of getting all the data out from QFM and use some Jupyter notebooks for just presentations. So this is a tornado diagram that is done using exactly the same data coming from QFM, but using a Jupyter notebook. And the last thing that we did for this example was calibration. That means, given a settlement evaluation in the field, how much are the parameters that induce that settlement? And we only look at the most relevant ones that came from the sensitivity analysis. So first we did deterministic calculations. And from the deterministic calibration, what we found is that actually there is not a unique solution for a particular settlement. So here you see two lines in red that corresponds to all the possible values that you can get for two different settlements. So that tells you that deterministic calibration for this particular problem was not appropriate. But if you do Bayesian calibration and you assume prior distributions for the most relevant parameters, then you find at the end that you can get how much would be the expected settlement given the uncertainties in the parameters. That shows you the difference between deterministic calibration and Bayesian calibration. Excellent example to introduce calibration and the different ways to do that. Second problem, let's get out of Q of M, and now let's go to EEUQ. For EEUQ, I wanted to deal with, again, a simple problem the students were familiar with, and we look at site amplification. So you have an input at the bottom of a soil profile, the waves propagate through the soil, and then you have the outcome, the output, which is the surface motion. For analyzing that, what you have to understand is transfer functions, something very well known. Very easy to do, particularly for a uniform soil profile. You have a very simple equation that you can use for that. And how do we calculate the amplification? The amplification is the peak ground acceleration at the surface with respect to the peak ground acceleration at the bottom. And what we want to do is to introduce uncertainty in the parameters that define the transfer function. Which are those parameters? Well, the thickness in this particular case, or the shear wave velocity, or the damping. So when you do that, then the amplification ratio, or the amplification is not going to be one unique value. You will have a distribution of values. And what we found is that for this particular case, it's not a single distribution. You have a bimodal distribution. Excellent example, again, not only to show the effect of the uncertainty, but also that you can have bimodal distribution. And finally, what I said is, why don't we try to bring this problem also to Q of M to do some calibration? What do I mean? This is an inverse analysis. So, for example, given the transfer function, how much are the values of shear wave velocity and damping that produce that transfer function? So we assume a distribution of those values, possible distributions, and then from that, we say for that distribution, these are the possible realizations of the transfer function in gray. The one that was given is the red one, so now you have to do the Bayesian calibration. So one thing to notice the universe of possible values for the amplification factors given the distribution that we have. And this is the prior distribution that you see here, and this is the posterior distribution. Notice how good the calibration is using Bayesian calibration. So you're doing inverse analysis, trying to get how much is the shear wave velocity and how much is the damping. And when you have these values, this is what you get when you compare what you were given with what is your estimation. Good example. Finally, I want to go into R2D homeworks. This was more difficult because R2D is more involved. So we went through several examples that are provided in R2D. One was basic HASUS, the other one, example 5, ground shaking and liquefaction. We did the hurricane and wind analysis, then we did the site response analysis. We invested 4 weeks into R2D to understand this. And then I want to show you just one of the examples that came from this, which was an example related to hurricane damage. So here, one of the students came out of the blue and said, hey, I am from Panama. I want to understand a little bit better damage induced by the Hurricane Maria in a city that was called Vieques. It's an island in Puerto Rico. So the first thing that we had to do was to get information about the hurricane. And we got a raster file with all the wind field information. Look at the values of the winds, 225 miles per hour. We had the raster file. And the interesting thing is that you can upload that into R2D. So boom, immediately we have the hazard into R2D corresponding to the problem that we want. The second thing is to look at the inventory of buildings that we want to evaluate damage. And R2D also provides some tools so that you can look at the national inventory, so that you can look at the assets for locations. The immediate thing that we found is that there is not information for Vieques that is in the national inventory. So here we had to do something different. So what we had to do is to say, hey, we have to build the inventory. Fortunately, also SimCenter provides a tool that is called Brails that allows you to get from the images from Google Drive. And from these images, you can import some Braille modules, and you can get how much the asset information for the location that you are interested. We did that. These are the footprints for all the buildings. These are several images that we got from Google Drive. And from there, we were able to get all the asset information that we brought into R2D. And then having the assets and the inventory and having the wind information, what we use is to do some damage and loss evaluation using the same tool that Adam was showing before, which is Pelican, that provides a set of rules that are based on hazards that allows you to evaluate different damage states. And from there, using the R2D QGIS tools, we were able to establish damage levels for the different buildings that we were interested. And the other thing I was interested is that we were able to not only use this in R2D, but import that into a regular QGIS. And QGIS also provides many additional libraries, for example, to develop heat maps and so forth, like I'm showing here. So this was one of the projects. I want to just close saying that every student had to develop a project. And the project had to result into a report. And the report has to be presented into Sphinx, into a Sphinx document. Sphinx is a Python library that allows you to take markdown script and transform that into a document following a style. I chose the style. The style that I chose was the SimCenter style, but they have to include only the information for the markdown scripts. So this is just I would say the initial page. If you go here, you will see this is the real document. So the settlement problems that I show you is all defined here. The hurricane problem is all defined here with all the notebooks and all the details on how to do things. And we had other examples, for example, for landslides, for liquefaction, and so forth. So this is the end of my presentation. I hope if you are interested in something like this, please don't hesitate in asking me for the whole material. This is all going to be available for people to use. So with that, that's my last slide. Thank you very much.
Okay, well, thank you, Pedro and Adam.